Thank you very much, Matt. I hope you can see my slides fine and you can hear me well. Okay, just confirm. Hello?
Yep, we can hear you. Thank you.
Perfect. Thank you very much. I'm going to shoot along. I'm going to talk about very high resolution simulations of the atmosphere that we're performing at ECMWF. And well, I'm going to start with the motivation. So why would we actually want to look into the atmosphere with 1.4 kilometer grid spacing? And you see the figure on the left here, which is showing basically the resolution level on the y-axis, going up from 250 kilometers to something like 1 kilometer now. And you see the peak performance that we had at ECMWF when we were actually able to kind of work with this resolution level on the x-axis, going from 500 megaflops to all the way to 4 petaflops that we have at the moment. And soon this is going to be upgraded to a new machine. And basically now we're reaching into the exascale, and to some extent we're hoping that we kind of will be able now to kind of go to 1 kilometer, which will then allow us to kind of represent deep convection and surface drag explicitly within the simulations. The one problem that you can see on the slide is also the sustained performance, which is kind of given on the top here. So if you compare the sustained performance and the peak performance, obviously you see that we work with something like a factor of 2 at the beginning, and kind of now we're down to a couple of % of the sustained performance in comparison to the peak performance. So there's some work to be done to really kind of make the most of those machines here. So basically more resolution typically leads to more skill in weather predictions. We are aiming for a better representation of topography with a high resolution simulations, in particular also of gravity waves that are spawned off the topography. We are hoping, or we will actually have an explicit representation of convection in the tropics. That's what we call typically storm resolving simulations, if you can basically switch off the deep convection parameterizations and represent those features explicitly. For the ocean, 1 kilometer would basically mean that you could represent all of the mesoscale eddies explicitly as well. So kind of you would be eddy resolving everywhere on the globe. And also you would have kind of good representation of tides as well. And last but not least, kind of when pushing the atmosphere resolution to something like 1 kilometer, you can also use basically the same resolution in the models that you have for the satellite data coming in, which kind of makes it much better to kind of compare the two and to actually simulate the satellite data into our prediction framework. So there are good reasons to go all the way to this kind of 1 kilometer resolution level. Just a couple of words on the model configuration that we're working with. We're working with the integrated forecast system, or IFS. We're working with the cubic octahedral grids with a truncation number of 7999, which basically means that we're kind of working with an average grid spacing of 1.4 kilometer, but we also have a grid spacing at the equator of something like 1.25 kilometers. Those simulations are performed with very high resolution topography, so we're smoothing out to something like 2.5 kilometers, which is still extremely high if you compare it to other centers. We're working with 137 vertical levels in the so quite also in the vertical, quite high resolution in comparison. We also have the full forecast complexity that we would have in our deterministic weather prediction models that is running at 9 kilometer, except that we're basically switching off deep convection parameterization schemes. However, we have no wave model or ocean coupled to the system here. The model is, as you may know, a spectral model, and we're kind of therefore working with the so-called semi-implicit semi-Lagrangian time stepping scheme, which allows us to kind of work with fairly long time steps, but I have more slides on this later on. We do run in single position. I'm sorry, John, I'm not going to go into much detail here. Basically, we can run the entire model in single position, and this is now also kind of basically prepared for operational forecasts, so we're quite confident that we actually get more or less neutral results in comparison to double position here. And we have runs that I'm going to show you, which are somewhere between 12 hours in the length and 4 months. Just to give you an impression of kind of other modeling centers who kind of running very high resolution simulations, and I'm sure this list is not complete at all. So apologies if you don't find your specific study in here. It can't be complete. But just to give you an impression, there has been really a seminal simulation by the NICAM group already a couple of years ago, where they kind of were already running 12-hour simulations with a sub-kilometer range on their machine. There has also been a 10-day model simulation with a sub-kilometer range in the grid spacing by the Cosmo group at Meteo Swiss and CSES, where they're basically running a dichord test. So this is kind of not really a realistic weather forecast simulations, but it has basically also the complexity of these simulations. And they also fixed kind of the northern and the southern pole area, because otherwise they couldn't do this with a limited area Cosmo model in principle. However, it's still an amazing study. And then there's also recently the Diamond model into comparison led by Björn Stevens and Masaki Sato, where they kind of collected the results of 9 different models running simulations in the atmosphere, of the global atmosphere, with a grid spacing of less than 5 kilometers for 40 days, and kind of looked into the similarities and the differences between the simulations. And finally, obviously, there are a number of large eddy simulations where you're just kind of focusing on a local area where you can go to much higher resolution, for example, 156 meters grid spacing over Germany in the HDCP square simulations. So basically, this talk is going to cover 2 publications that have recently appeared. One of them is basically about the investigation how different model changes to the configuration of the 1 kilometer will actually lead to different results, and kind of what the best optimal setup for our simulations would be to run it at 1 kilometer. And also one simulation where we kind of summarize the results from a very long time integration, like a seasonal integration at this very high resolution level. So just a couple words on the model that we're working with. I think most of you will know, but we're working with the spectral transform model, which basically means that we kind of represent all of the fields both in grid point space, the cubic octahedral grid, but also in spectral space. So we basically do a Fourier decomposition on the sphere. And to kind of to change between those 2 worlds, you basically need fast Fourier transformation and so-called Legendre transformations. And you kind of keep those 2 worlds because you want to calculate semi-Lagrangian advection in the grid point space and the physical parameterization schemes in the vertical in the grid point space, but also nonlinear terms and the product of terms. However, you also want to kind of calculate horizontal gradients in Fourier space, which is then kind of basically comes for free. And also there's you can basically use semi-implicit calculation within spectral space, which is extremely efficient in terms of that you work with very long time steps, but it's kind of very computationally cheap. And finally, also diffusion, for example, is going to be very cheap in spectral space. So just a couple of cons and pros for the spectral representation. You may have seen plots of spectral ripples in spectral models. So basically you get a lot of fine scale ripple features often in those models. Those models seems to be more suited for hydrostatic equations. So there's a hydrostatic approximation in the atmosphere. And those models are typically designed for hydrostatic equations. However, if you kind of go to this very high resolution simulations where delta x is basically varies to this static approximation breaks down to some extent, we still it's a bit hard actually kind of to work with non-hydrostatic equations in those spectral models. And another famous problem is the so-called Legendre transformation, because this scales with n cubed, and n is the number of grid points at the equator. And as you basically increase resolution, the Legendre transformation will take more and more of the ratio of your computational cost. And basically, people often say that this is kind of the problem that is kind of finally going to kind of put spectral models out of competition. And then the code is obviously also kind of quite complex, as you have to kind of secure those 2 worlds in parallel. On the pro side, you have global connectivity between the different scales, and you have access to the different scales as well. You can easily calculate spectra, for example. You basically, via the spectral space, you also have a very efficient compression of data, and you can easily kind of compress data. As I said, you have this kind of semi-implicit semi-Lagrangian solver, which is very efficient. It allows you for very long time steps. You can also avoid this kind of n cubed by going to the so-called fast Legendre transformation, which is a bit of an approximation taking place, but it's kind of not this n cubed scaling anymore. And we don't see a big degradation of results. So therefore, we're going to work with this FLT, the fast Legendre transformation, in all the simulations, all the high resolution simulations that I'm going to show you. It's easy to implement diffusion and global fixers. And also the use of realistic topography without excessive filtering at smaller scales is kind of quite doable. There are a couple of kind of points of conventional wisdom that kind of people in the community have stated quite a number of times, and that I kind of try to address with this talk to some extent. One of them is that simulations at order of 1 kilometer resolution will need to be non-hydrostatic, because you will be basically see big differences between non-hydrostatic and hydrostatic simulations, and the hydrostatic one is an approximation, so the non-hydrostatic ones are basically the correct ones. Second of all, the time steps should be less than 60 seconds if you are at a resolution of something like 2 kilometers. And also, spectral methods will not be competitive if resolution is increased due to this problem of the n-cubed scaling with wave number. So let's see how much of this is true and how much is not. This slide is giving you the relative cost for the different model simulations. So on the top left, on the A, you basically see the fraction of the different costs that we have in our operational weather prediction simulations at 9-kilometer resolution with full I/O and full coupling. And as you kind of now go on our own machine at ECMWF to a simulation, which is kind of the same one that I'm going to use for scalability comparisons, so basically no wave model, no NEMO model, no I/O, you end up with something like the fraction B. And you will see that 41% of the cost is actually coming from the transformations, which is obviously a big chunk of cost. Then if we go from our own XC40 machine at ECMWF to Pitt-Stein, and we now push resolution to 1 kilometer, you will see the plot on the top and bottom left. And you will again see 41% for the transformations. This is mainly due to the better network on Pitt-Stein. It's not just, the cost is in principle higher in terms of computation. And if you now go from the hydrostatic case for C to the non-hydrostatic case, you will see that basically the transformation is kind of getting more expensive for the simple reason that we need to go at least twice through the transformations in each time step. So therefore, basically the relative cost of the transformation is getting more expensive. And if you now think about the total cost between a hydrostatic and a non-hydrostatic simulation on Pitt-Stein, you will see that basically the hydrostatic simulation is kind of reaching something like 0.2 simulated years per day if you really scale to the size of the machine, whereas the non-hydrostatic case is kind of almost a factor of it's a factor of two slower basically, because you have to kind of make this additional iteration in between grid point and spectral space. So basically, this means that we have quite a big intention to kind of keep everything in hydrostatic mode, right? So let's test how kind of the different model options are actually going to impact performance and quality of the solutions. So let's make a couple of different tests with a couple of different model simulations. We can either use hydrostatic or non-hydrostatic cases. We can work with or without topography. We can work with 137 vertical levels or 62 in this case, admittedly, because we couldn't afford to kind of go much higher for the non-hydrostatic cases on this machine. And then also we use finite element discretization in the vertical, or we use finite different discretization in the vertical, kind of two different options. For the non-hydrostatic case, we actually need to work with finite difference. And then there's also the option of working with different time steps, like 120 seconds, 60 seconds, or 30 seconds, and a different number of predictor character iterations in your simulation. So these are some results for the vertical velocity fields over Indonesia. And you basically see the simulation with 120 seconds time step on the top left, and you will see kind of that it's a bit popcorny. So there's definitely something going on, which is probably due to the very long time steps. However, if we go down to 60 seconds, you can have the field looks much better and much finer scaled. And there's not too much of a difference between the finite element 60-second simulation on the top right and the finite difference 60-second simulation on the middle in the middle left. And then also the differences between the hydrostatic and the non-hydrostatic case here is comparably small. If you now go to 30 seconds time step and no topography, we can still see a bit of a difference here in comparison to the ones with topography, mainly caused probably by topography. But also again, like the hydrostatic and the non-hydrostatic case are extremely similar again. So basically, there doesn't seem to be a big difference here. Also satellite simulators. So again, over Indonesia, you see the satellite data basically in the top left. You see the deterministic high resolution forecast at ECMWF on the top right. And then you see the other 6 simulations. Again, the case with 120 seconds is kind of quite popcorny and not too realistic. If you now go to 60 seconds, it's going to look much better. And again, basically, if you have the cases with hydrostatic and non-hydrostatic, both for the 60 and for the 30 seconds time scale, you won't see much difference here. So basically, in the diagnostic that we looked into, the non-hydrostatic effects did not seem to be kind of the most important model choices. There are other model choices like the vertical discretization schemes and the time steps that is kind of much more important. And also, from all that we can say, the time step of 60 seconds really behaves well. 120 seconds is kind of probably too much, but 60 seconds basically seems to be in a good compromise between performance and quality. So if you look into the energy spectra, you can see those results here. On the left for 200 hectopascal, on the right for 500 hectopascal. Basically, you see this kind of scaling behavior of -3 scaling for large scale and -5/3 for small scales that you want to see, except for this orange simulation here. And this orange simulation is actually the model setup that we use in operational predictions at 9 kilometers. So if you go to 9 kilometers, you don't really make this scale transition from -3 to -5/3 that is kind of expected from theory. However, as you kind of increase resolution to 1 kilometer, you will basically see the scale in separation, or sorry, the change of the scaling behavior. And this is exactly what you want to see. Also, if you kind of think about the effective resolution levels, what you see is that the spectra is kind of shadowing off somewhere between 5 and 10 kilometers. So that's also the range of what you would expect in terms of the efficient resolution of those simulations. And one thing to note is that we have a slight increase of the spectra for the non-hydrostatic case with 60 seconds. So there seems to be something fishy going on here, and we kind of are now also exploring different ways of looking at high approximation. Sorry, non-hydrostatic simulations. The probability density functions of the vertical velocity that we see for those different simulations. And basically, I don't want to go into too much of a detail here, but I basically want you to get the message that those distributions look actually very different for the different simulations. So basically, I mean, this is just a logarithmic scale, so most of the points are going to be basically around 0. However, for the more extreme vertical velocities, the distribution looks very different for the different simulations. And basically, the problem is now that we don't really know how the truth of the PDF should look like. But also, we found when looking into the Dueben simulations that actually we also, again, between the different model simulations, we get very different results. So even though, for example, cloud features are really looking very much like observations, and people argue that we have passed the Turing tests where it's basically impossible for domain scientists even to distinguish between a forecast simulation and the observations from the satellite. If you think into the right detail, basically you will see very big differences. And also on the not so great side, if you calculate the forecast error of those very high resolution simulations, you will actually find, so both on the left, you can see the forecast error for geopotential height at 500 hectopascal, and on the right, you see temperature at 850 hectopascal. What you see is that the lowest error comes from the magenta simulation here, and that's unfortunately the 9-kilometer case. So basically, this means there's no free lunch. Even just a normal increase in resolution is not going to give you extremely just suddenly a jump in forecast error down. And actually, if you think about deterministic cases, it may actually increase variability of those simulations, because now convection is resolved explicitly, which actually may decrease your root mean square error results. So basically, storm resolving simulations will still require a lot of model developments and will not improve predictions straight out of the box. So you can say that's a negative result. However, it's what we expect. So at ECMWF, always when we go from a coarser resolution to a finer resolution, it will take some time and some model adjustments to actually make the most out of this resolution increase. Okay, in terms of scalability, what you see on the left are forecast days per day for the different numbers of nodes for two different machines, Pete Stein and Summit. You have Pete Stein with a non-hydrostatic case reaching something like 30 forecast days per day without I/O and with 62 vertical levels now. If you go to the hydrostatic case, we reach something of almost 70 forecast days per day. And if you go to Summit and basically use a hydrostatic, you reach more than 100 forecast days per day for this 1 kilometer case. This is quite extraordinary, I would say. So it's much more than we would have expected, let's say 5 years ago, to reach with those very high resolution simulations. And also, the plot on the left doesn't even use the GPUs yet. However, if we are going to use the GPUs, we are still going to get a quite significant performance increase. So these are simulations just with a transform package, kind of transforming there and back again on summits, either with the CPUs, basically using all the CPUs and nodes, and the nodes kind of increase from left to right on the x-axis. The CPUs are orange, and all the GPUs are used on the nodes in green. And you will see that you basically get quite a significant improvement in terms of performance for the transforms package now if you kind of switch to the GPUs. So there's more to come. And basically, what you should get from this slide is to some extent that spectral models are still very competitive at this level of resolution. So this kind of number of more than 100 forecast days per day is really kind of among the top models at this resolution that you could hope for. So I don't think it's kind of it's early enough to kind of say that spectral methods are going to be dead if you kind of further increase resolution. The second half of this talk is going to be about this kind of second publication mainly, and this is basically results that we were able to kind of get via an Inside 20 grant, where Niels is a PI here, and Niels has really performed the simulations and has done most of the work, so praise to him. I'm going to work with this kind of hydrostatic finite element version and the 60 seconds time steps from now on. So what we were able to do basically with this kind of inside grants were to kind of run a model simulation at this 1.4 kilometer grid spacing for 4 months and not just kind of a day to make some evaluations. So first of all, the Turing tests, as I said before, basically people talk about the Turing tests that even domain scientists are not able to kind of distinguish anymore between a model simulation and observations. So here we have the 9 kilometer case, the operational setting of IFS on the top left. You have the 9 kilometer case without deep convection on the top right. And you will basically see that in the tropics, you see popcorny behavior. So this is kind of 2-coarse resolution, and you basically see that the convective cells are too big. As you go to 1 kilometer, those popcorny behavior goes away, and it looks very, very realistic, really. You also have a kind of a sharper ITZZ, which is good. And if you now look into the observations are still a bit sharper. However, most of the difference is actually coming from the radiative fields that are kind of averaged over 3 hourly intervals in the model simulation. So you would really, if you would compare like with like, you would probably even have less smearing in those fields. If you run a 1 kilometer case that you haven't kind of really evaluated to all the details yet due to the cost for 4 months, it's a bit of a gamble in terms of what's going to happen if you kind of run it for a very long time. So there is a risk that it may fail after 2 months, which it didn't, and actually it performed very well in terms of the mean fields. So what you see here is a zonal mean, zonal wind for different simulations for the 9 kilometer case. 9 kilometer case without deep convection, 1.4 kilometer case, and the ER5 reanalysis. So that's kind of the truth. And what you see is basically that the mean fields are fairly similar between the simulations, which is a good thing. So the simulations with 1.4 kilometer grid spacing is consistent with simulations at 9 kilometer and reanalysis data. Also, if you look into precipitation, you get quite good results. And I think I'm running out of time if I interpret the fact that I just got a chat correctly. So I'm going to jump over this. If you look into updraft helicity, you may kind of be able to kind of get some information of what you could do with those simulations in terms of tornado predictions, because that's basically, and tornadoes are basically driven by upward helicity. And if you think about the 9 kilometer case, you get basically a time mean of this quantity on the left. The 9 kilometer case without deep convection is giving you the result in the middle, and the 1 kilometer case is giving you the result on the right. And if you think about the season that we have, basically this is exactly the area where we would expect tornado activity. So maybe there is actually some benefit here also to kind of basically get more closer to the tornadoes if you kind of increase resolution. So the next steps to be looking into after this one simulation, we want to kind of go to coupled simulations, and this will be done in first of all, in the framework of Diamond winter cases. So the next version of Diamond is going to look into coupled simulation. So we're going to have a 4 kilometer simulation, IFS simulation coupled to a quarter-degree ocean plus the wave model. We're also going to explore machine learning to increase efficiency. And we're also going to explore half precision to increase efficiency, in particular for the Legendre transformations. And as I said, I'm probably running out of time, so I'm going to skip over those slides mostly. For machine learning, we want to in particular look into the emulation of the radiation scheme, It's also something that Matt Norman, our chair of the session, has actually done in the past, and other people as well. And we also have a project going on together with NVIDIA where we're kind of exploring this direction, getting quite good results. And also, I mean, for the future, we are also interested to also do preconditioning with machine learning. And here we have a collaboration going on with the University of Oxford, where we get quite interesting results, where we basically use machine learning tools for preconditioning of our linear solver that we would work with in our grid port version of the IFS. And deep learning, and reduced numerical precision. Basically, the question is whether we can also use deep learning hardware for conventional modelings, because there has been, as you all know, a lot of progress towards like very low numerical precision and very used for dense linear algebra. And if you think, for example, for the tensor core accelerators on NVIDIA Volta GPUs, you all know that the peak performance is kind of just fantastic that you get if you could use in principle half precision and dense linear algebra, and in particular matrix multiplications. So can we actually use those tensor cores for our models? It turns out that the Legendre transformation, so the most expensive kernel we have, isn't doing nothing else than a standard matrix multiplication, and just many of them. So the question is whether we can use half precision here. And it turns out if we rescale the input and the output fields of the Legendre transformation, which is linear, so it's no problem to do this, we can actually use half precision. And then we also get fairly good results in terms of the forecast score. So this is results that we published at the PASS conference last year, and it shows the forecast error for temperature at 5 hectopascal for different areas of the globe. And basically within the level of uncertainty due to limited statistics, we get the same level of results. Some room for interactions. We have a workshop next week about machine learning for observations and predictability. That you're very welcome to join. And we also have just learned that our Maelstrom UHPC proposal was successful. So we're going to kind of look into a co-design effort to kind of build customized machine learning hardware or computing systems for machine learning applications in weather and climate simulations. And in this context, we're also hiring at the moment. So please let me know if you're interested, not only at ECMWF, but also with our 6 partners in Europe. And finally, the conclusions. So I hope that I convinced you that it's actually kind of quite difficult to make those 1 kilometer cases, but with a great team of specialists and with kind of a bit of endurance for data handling and other problems, you will actually be able to perform those simulations. And those simulations now become available. So it's really that we can now perform something like a 4-month integration without without huge problems. Also, higher resolution is indeed improving many things, and the runs are clearly passing the Turing test. So it's kind of an amazing level of details in those simulations. But what does it actually mean, right? I mean, basically, the differences are still very big between model options. So we still will require a lot of development here. For example, the forecast errors are also not necessarily improved. And just to give you one example, when we first submitted the JSMJ paper, we actually had a bug in the pre-processing of the topography fields, which basically erased all topography. We did not even realize on the level of diagnostics that we're working with 12 of 24 hours simulation. So it really requires more diagnostics, more quantitative studies, and to kind of really adjust the model components and, for example, the shallow convection parameterization schemes to the new world where the deep convection parameterization scheme is switched off, if you want to really make the most out of this high level of resolution. However, if you can do this, you will get actually extremely nice simulations that are going to be very feature rich and very interesting, and that are going to push weather and climate predictions in the future, I'm sure. And with this, I want to thank you for your attention. So one question, how to control the error increase in steep terrain using the spectral model when the spatial resolution goes to 1.1 kilometer? I mean, we have been working with very steep topography already. So this, as I said, we kind of smoothed the topography to something like 2.5 kilometers, and it's not. I mean, it's a bit of a trial and error thing. To some extent, you basically run the model and look whether it's going to be stable or not. But in particular for the hydrostatic case, I don't think that's an extremely big problems. And we don't basically. I think with a normal configuration, we actually kind of were able to run this case. For the non-hydrostatic case, we had to play a bit with the time stepping scheme, but again, I don't think that's going to be a huge problem. So Luca is asking, so your code scales better on V100 than P9. In my experience on GPUs, you lose scalability faster than on conventional CPUs. Could you comment on that? I mean, this was basically for the Legendre transformations, where you have basically a large number of matrix-matrix multiplication. So I think it's more about I think the how to phrase this. I don't know. I don't think. I mean, I don't think we had big problems here. I think the big questions still is basically how to kind of switch between CPUs and GPUs in a very efficient way for those transforms. I wouldn't. The scalability seems to work quite well. And then Sarat trying to understand performance results on Summit GPUs. What's ported? Transforms, PKG. How does it compare to the overall model in terms of computational cost? So yes, so we ported the transform package. So that's basically almost that's 40% of the cost for the hydrostatic case and more than 50% of the cost for the non-hydrostatic case. But that's it for now. So basically that's the one that we kind of ported. For the rest, we're kind of really looking forward to our network emulator for the radiation scheme, for example, that would also kind of bring portability for free. And we're also having a big effort for those of you who know about the scalability project at ECMWF to also kind of port as much as possible for the rest of the code GPUs as well. I hope this answers your question. Thank you.